Okay, so this week's discussion is on AZT, the antiretroviral that works. We should remember, though, that much of my research that I came across discussed how AZT is really a part of a combination therapy and that there are lots of different steps that make it such an effective antiretroviral drug. So, we're going to take a look at those steps now. So AZT is known as a nucleoside analog or a nuke for short. It has a couple of the names. They've called it retrovir or ziduvudine. It can also be taken as a component of the tablets of Combivir or Trizavir. And what it does is it reduces the activity of the reverse transcriptase. And so that's kind of key to all of this, that the reverse transcriptase cannot work in the retrovirus. So virus replication cannot take place. Um, and so people don't get sick. And if that enzyme doesn't work, then AZT is doing its job. So we're going to keep on looking at it in more detail and with some images. Um, excuse me. So it's part of HART therapy, which stands for highly active antiretrovirus therapy. And what it does is it creates a mitochondrial dysfunction. And then this mitochondrial dysfunction is key to the beginning of it all. So that's just a key component of HART. And it was mentioned in our prompt that there's an enzyme, AZTTP, which is AZT triphosphate, and that's the host enzyme that enables AZT, the drug, to work. And that's what disrupts the function of that mitochondria and leads to viral cell death. Um, you should also note that AZT is a thymide analog. So when you're thinking about your amino acids, and it's converted to the active form of the enzyme by phosphorylation. And some other enzymes to remember in the process are TMPK or human thymidylate kinase, so the kinase group, and then that, as I've mentioned before, that it's blocked to be effective. Sorry. Okay, we'll just move me around. So if it's the enzymes that really help the AZT work. Don't forget about the kinase. Don't forget about the triphosphate. Don't also forget about the primase and the polymerase. They're always used in RNA and DNA synthesis. And then let's just go ahead and take a look. Hopefully, I won't run out of time here at the intracellular processes on the next few slides. So I really like these images on the left and the right. Mostly I put the stop signs on the right and I put just the generic kind of broad images on the left. So you can see the HIV envelope, you can see the enzymes inside the capsid, you can see the glycoproteins on the surface of the cell. And then on the right, you can see the antiretroviral, the HIV drug that inhibits it from entering the CD4 cell, and you can see the big stop sign. So it blocks that HIV envelope from fusing with the cell membrane of the CD4 cell. We'll just move me again. And then you have the reverse transcriptase. This is just a kind of more detailed image, all right, bigger really. So you can see the helix of the reverse transcriptase, and you can see it trying to get into the CD4 nucleus, but on the right-hand side with the stop sign, you see that the NNRTIs and the NRTIs block that HIV RNA to DNA transcription translation process. Sorry that it keeps doing that. Okay, and then this might be one of the last slides. So this is talking about integrase, another enzyme found in HIV and retroviruses. The integrase tries to insert itself in the viral DNA and of the CD4 cell. Integration is a critical part of the HIV life cycle, but the antiretroviral drugs, the